Hello everyone, welcome in the video lecture of Integrated Circuits KEC 501. I am Goel, Assistant Professor in the Department of Electronics and Communication Engineering, Ajay Kumar Garg Engineering College. In today's lecture, we are going to discuss the gain and the frequency model of op-amp IC 741. Let's have a look of op-amp IC 741. The op-amp IC is a 8-pin IC available in dual inline package. The meaning of dual inline package is that we have symmetrical amount of pins at both the sides. The op-amp IC is a 8-pin IC where we have offset null at pin number 1 and 5. Pin number 2 is to provide the inverting input. Pin number 3 is to provide the non-inverting input. Pin number 4 is to provide the negative power supply. Pin number 7 is for positive power supply. Pin number 6 is to observe the output signal, and there is no connection at pin number 8. As we know that op-amp operational amplifier is a very high gain direct coupled amplifier, differential amplifier, which is basically used to perform the mathematical operations like addition, subtraction, integration, differentiation, and mainly for the amplification of the weak signals. This is one of the oldest IC and the most popular op-amp IC. Here we have the complete internal circuit diagram of op-amp IC that we have seen in the earlier slide. In the internal circuit diagram of op-amp, we have total 24 transistors from 1 to 24, total 11 resistor and 1 capacitor. This entire internal circuit diagram of op-amp is divided in 5 stages. Namely, the first one is called as bias circuit of op-amp IC 741, then input stage, then the second stage, output stage, and output short circuit protection circuitry. Out of these 5 category or the division of this complete internal architecture of op-amp IC 741, we have 3 main stages, that is input stage, second stage, and the output stage. Let's have a look which part of this circuit constitute which stage. Starting from the leftmost of the circuit diagram, first we have the bias stage of this op-amp IC 741. The bias stage includes transistor number 12, resistor 5, and transistor number 11. These 3 components are responsible for generating a reference current for this entire internal circuitry of op-amp IC 741. Here we have the reference current, which is around 0.73 milliampere, which serves the purpose of reference current for this complete op-amp IC 741. Then next we have transistor number 10, 9 and 8. These 3 transistors are responsible for providing the biasing to the input stage. The input stage constitutes transistor number 1, 2, 3, 4, 5, 6 and 7. Along with these 3 resistors R1, R3 and R2. So in the input stage mainly we have 7 transistors from transistor number 1 to 7, and the biasing of the input stage is provided by transistor number 8 and 9 along with transistor number 10. We can observe here that transistor number 8 and 9 are forming a current mirror circuit. Transistor number 12 is forming a current mirror with transistor number 13, and transistor number 11 is forming a current mirror, which is Widler current source, with transistor number 10. What is a current mirror circuit? Current mirror circuit is a kind of circuit which is used to replicate the input current at the output side. That means whatever current is flowing at one side of the circuit, we will get the same amount of current at the another side of the circuit. The main aim of the input stage is to convert the dual-ended signal into the single-ended signal. What is dual-ended signal? In op-amp, we have provision to apply input at the inverting terminal, that is pin number 2, and at the non-inverting terminal, that is pin number 3. The pin number 2, which is called as inverting terminal, is internally connected with the base of transistor number 2. So this is the basically our pin number 2, and the pin number 3, which is non-inverting terminal, is internally connected with the base of transistor number 1. Okay, so These 4 transistors are then 4 and 3. Transistor number 3 and 4 are connected in differential amplifier configuration. These 4 transistors are basically responsible for converting the dual-ended signal into the single-ended signal and to provide a very high input resistance. Further, transistor number 6, 5 and 7 are behaving like the active load for this input stage. Moving forward towards the second stage, the second stage consists of transistor number 16 and transistor number 17. The biasing of this input stage is done by transistor number 13B. Here in the second stage, we have one more component that is called as coupling capacitor of value 30 picofarad. In the entire internal circuit diagram of op-amp, we have only one capacitor and it is connected in the second stage of the op-amp IC. Then moving towards the output stage, the output stage consists of transistor number 13A, 19, 18, 23, 14 and transistor number 20. Out of these 6 transistors, transistor number 14 and 20 are the main component of the output stage, which is responsible to provide the amplifier with low output resistance. While the transistor number 13A, 19 and 18 and 23 are providing the biasing to the main output stage, which is formed by transistor number 14 and 20. Okay. Then transistor number 15, 21, 24 and 22. These 4 transistors are the part of short circuit protection circuitry. What is short circuit protection circuitry? These 4 transistors normally remain off, they do not conduct. They conduct only in the event when there is a flow of large amount of current in the output stage, that is either through transistor number 14 or transistor number 20. For example, if the current across transistor number 14 exceeds a particular value due to some short circuiting condition, then this transistor number 15 will turn on and will steal the excess base current from the base of transistor number 14. So 15, 21, 24 and 22 are called as the part of short circuit protection circuitry, but they do not conduct in normal situations and conduct only in the event of any short circuiting situations. So this is the brief introduction of the internal circuit diagram of op-amp IC 741, which is divided in 5 stages: bias circuit, input stage, second stage. The second stage, the function of the second stage is to provide the gain to the operational amplifier. The maximum amount of gain that we will get from any of the stage is the second stage. That is why second stage is also called as gain stage. The output stage and then the output short circuit protection circuitry. Now let us discuss the overall small signal gain model of op-amp IC 741. What is overall gain model of op-amp IC 741? As we know that the open loop gain of operational amplifier is ideally infinite and practically it is very high. So with the help of internal circuit diagram of this op-amp IC, we can actually calculate what is the practical value of gain for op-amp IC 741. How we can calculate the overall gain of op-amp IC? In the last slide, we have seen that the complete internal architecture of op-amp IC is divided in majorly in 3 parts. That is input stage, second stage and the output stage. The overall gain model consists of the small equivalent small signal model of each of these 3 stages. The small signal model of input stage, the small signal model of second stage, the small signal model of output stage. As we also know that op-amp is a high gain DC amplifier. The meaning of the word DC here is direct coupled and not the direct current. What is the meaning of direct coupling? The meaning of coupling is that the output of one stage is behaving like the input of another stage. So when we are saying that first we have input stage, second stage and then the output stage, then the output of input stage is behaving like the input of second stage, the output of second stage is directly connected to the input of third stage. In this way, three of these stages are cascaded with each other. So, if we want to find out the overall gain of the op-amp IC 741, we can cascade these three stages. After cascading these three stages, with the help of their equivalent small signal model, we will get the overall small signal gain model of op-amp IC 741. Here, if we look at this circuit diagram, first we have the differential input resistance, then the transconductance of the input stage, then the output resistance of the input stage. It is cascaded with the second stage, which is also known as gain stage. This is the input resistance of the second stage, transconductance of the second stage, the output resistance of the second stage. Then further, it is cascaded with the output stage. Here we have the input resistance of the output stage, output resistance of the output stage, and its transconductance value. The purpose of the input stage is to provide the amplifier with very high resistance, to convert the dual-ended signal into the single-ended signal, and to provide the gain. The main function of the second stage is to provide the additional input resistance and the major amount of gain to the op-amp IC. The function of the output stage is to provide the amplifier with low output resistance. From the output stage, we do not get any amount of gain. The gain that we are getting from the output stage is approximately 1. So, the value of gain or the amount of gain which is required for op-amp IC is majorly coming from the input stage and the second stage. To calculate now the overall gain value of the op-amp IC, how we can calculate? Let us consider that at the output we have connected a load resistance of value 2 kilo ohm. By considering the value of load resistance 2 kilo ohm, we have done this calculation. Here, the overall gain of this op-amp IC can be expressed with the help of this expression, where the final output voltage upon input voltage is equal to the multiplication of gain of individual stages. First, we have the gain of input stage, then second gain of second stage, then the voltage gain of output stage. On multiplying the gain of individual stages, we can get the overall gain of op-amp IC. Here further we have mentioned the expression for gain to find out the gain of individual stage, which is given by minus GM1, the parallel resistance of R01 Ri2, where R01 indicates output resistance of first stage, Ri2 indicates input resistance of second stage, then minus GM2 R02 GB03 RL divided by RL plus RL plus ROut. RL we have considered 2 kilo ohm. On putting value of each and every term in this particular expression, we can calculate the overall gain value. The value of the individual parameter we can obtain with the help of a small signal analysis, that is also called as AC analysis of input stage, second stage and the output stage. Okay. So, on putting the value of each parameter in this particular expression, we will get the overall open loop gain of op-amp as 243147 volt by volt, because this is the voltage gain. So, in the numerator also we have the voltage term, in the denominator also we have the voltage term. So, basically it is unitless. This is the practical value of gain of op-amp IC 741, which is 243147 and infinite ideally. When we will convert this value in dB, we will get the overall op-amp gain, open loop gain of op-amp is 107.7 dB. This is the practical value of the gain. This is the actual value of the gain that we can achieve with the help of op-amp IC 741. Okay. Next is the frequency response of op-amp IC 741. What is the meaning of frequency response? how we can calculate the frequency response? Frequency response is nothing. It is a curve between the variation in the frequency and the open loop gain or the gain of that particular circuit. So, the frequency response of op-amp IC741 is a graph or a plot between the open loop gain versus frequency. Ideally, the gain and the bandwidth of op-amp is infinite. What is the meaning of infinite bandwidth? That it will amplify all the signals with equal amount of gain, having frequency minimum to maximum. Okay, but practically it doesn't happen. Practically gain decreases with the change in frequency. When we increase the frequency, then the gain starts decreasing. This decrement in gain is called as roll-off rate. After a certain frequency, this roll-off rate decreases, and the reason for the decrement in gain is the presence of capacitive components. The capacitive components is due to the parasitic capacitances formed in the BJTs or due to the connections we are using to connect one stage to the another stage. So, these capacitances, parasitic capacitances, are responsible for decreasing the amount of gain with increase in frequency. At up to a certain point, we can compensate this decrement in gain. To compensate the decrement in gain, we have a term called as frequency compensation. The frequency compensation can be done in two ways, internally and externally. In op-amp IC741, we have the provision to provide this frequency compensation internally with the help of Miller compensation technique, and that is done with the help of a capacitor of value 30 picofarad, which is connected in the second stage that we have seen in the internal circuit diagram of op-amp IC here. So, internal frequency compensation, there is a provision of internal frequency compensation in the second stage with the help of this coupling capacitor. Here this coupling capacitor is connected in the negative feedback path in the second stage, and the technique that we are using for providing the internal frequency compensation is Miller compensation technique. So, let us first observe the overall frequency response of op-amp IC741, then we will see how much compensation we can provide with the help of this coupling capacitor with the help of Miller compensation technique. This is the graph frequency response curve for op-amp IC741. It is a curve between the frequency and the gain, open loop gain of op-amp IC741. We have observed in the gain model that the open loop gain of op-amp is 107.7 dB. At zero frequency or at minimum frequency, we are getting the maximum gain. But when we are moving forward towards the higher frequency, this gain will start decreasing. At a certain point, this gain first decrease will decrease by amount of 3 dB, which is called as 3 dB frequency. This point will occur at 4.1 Hertz. How we are getting this 4.1 Hertz? We'll discuss after this curve. So, the frequency at which gain becomes 3 dB down from its maximum value is called as 3 dB frequency or crossover frequency. After that, the gain will start decreasing at a rate of minus 20 dB per decade. Here, because we have only one pole, so for the first order, after cutoff frequency, this is also called as cutoff frequency. 3 dB frequency is sometimes also called as cutoff frequency. So, for the first order, the decrement in the gain after cutoff frequency is minus 20 dB per decade. That means, for every 10 times change in frequency, we will observe a decrement of 20 dB in the gain from the maximum value. Then, this value will come or will decrease to up to 0 dB. 0 dB means 1. So, there comes a point when gain becomes exactly 0 dB or 1. That means, we will not get any gain after that particular value. That value of frequency at which we are getting gain 0 dB is called as unity gain bandwidth. What is unity gain bandwidth? the frequency at which gain becomes 0 dB or unity. Okay. So this is the frequency response curve of op-amp IC 741. This is how the op-amp IC behaves on increasing the frequency and gain behaves on increasing the frequency. Now let us discuss how we have achieved this unity gain bandwidth value 1 megahertz for 741 op-amp IC. This is the overall gain model of op-amp IC 741, where this coupling capacitor is connected in the negative feedback path in the second stage. This coupling capacitor is providing the frequency compensation with the help of Miller compensation technique. So first we are required to calculate the overall input capacitance. The overall input capacitance can be calculated with the help of this expression given by Miller compensation technique, Cc1 plus mod of A2, where Cc is the value of this coupling capacitor, A2 is the value of gain of second stage. So when we'll put this value of gain of second stage and coupling capacitor value, we will get the overall input capacitance, which is around 15480 picofarad approximately. Okay, the value of the coupling capacitor is 30 picofarad and the gain of the second stage is around 526.5. We have observed this value here also. This is the value of the gain of the second stage. So the overall input capacitance is 15480, which is quite high. Then the resistance, the total resistance we can calculate by considering the parallel combination of output resistance of input stage and input resistance of the second stage. These two values, as I told you, can be calculated with the help of a small signal model or the small signal analysis of second stage and the input stage, which will come around 2.5 mega ohm. We know the value of formula of frequency is 1 upon 2 pi RC. So when we will put the value of overall input capacitance and the total resistance, we will get this value 4.1 hertz. This is the very first frequency at which we can observe the decrement in the gain, that is of 3 dB from the maximum value. Okay. Further, we want to calculate the unity gain bandwidth value. This can be calculated by multiplying this value with its open loop gain value, that is 243147. When we multiply this value 243147 with 4.1, we will get the unity gain bandwidth value as 1 megahertz. So practically the gain bandwidth product of op-amp IC we can say is this value 1 megahertz. Here we have the simplified model of op-amp IC 741. In this model, what we have done, we have drawn each of the three main stages: input stage, second stage and the output stage. Input stage is mainly responsible to provide the high input resistance, which is indicated here, the input differential resistance. Then because the gain of the second stage is very high, we have neglected the output resistance of the input stage and the input resistance of the second stage. This is indicating, this infinity symbol is indicating that the gain of the second stage is very high. Here the capacitor is connected in the negative feedback path, providing the frequency compensation internally. Then it is showing the unity gain output stage. +1 is the indication that the output stage has no gain, or the value of the gain is unity. That means it is processing what is getting as it is. The function of the output stage is just to provide the low output resistance. So this circuit diagram is called as the simplified model of op-amp IC 741. With the help of this model, we can again calculate the value of unity gain bandwidth. If we'll observe this particular circuit diagram, we can say that it is in inverting configuration. We know the relation between the output and the input voltage for inverting configuration is what? V out is equals to minus of feedback resistance upon input resistance into V in. This is the relation of output and input voltage for inverting configuration. Here the value of the current is GM1 Vi. No current will enter inside the op-amp because of very high input resistance. So the value of current flowing in this branch will be equal to the value of current flowing in this branch. If we'll mention the value of both the currents, then GM1 VI is equals to the current, let's say I is flowing in this branch. I is equals to 0 minus V out divided by the resistance or the capacitive reactance across this capacitor, that is 1 upon S into C. How we can mention the capacitive reactance? 1 upon Cc. So when we will equate the value of both the currents, what relation we will get between the output and input? It is equal to the Gm1 upon S into Cc. We know that S is equals to J omega. Replacing S with J omega, our equation will become Gm1 J omega upon Cc. Taking the magnitude of this term, what we will get? We will get this value is equals to Gm1 upon omega Cc. Okay. In the previous frequency response curve slide, we have seen what is unity gain bandwidth. Unity gain bandwidth is the value of the frequency at which gain becomes 0 dB, and it is denoted with omega t or ft. So at omega is equals to omega t, the value of this gain will become what? 0 dB, which is equals to 1. So we can replace in this equation. In this equation, we are replacing omega with omega t, then the value of this gain will become 1. 1 is equals to Gm1 upon omega t into Cc. So what omega t will come out? Omega t will become Gm1 upon the value of coupling capacitance. The value of coupling capacitance is 30 picofarad. The value of Gm1, that is the transconductance of the input stage, this can be calculated with the small signal analysis of the input stage. It is 0.19 milliampere per volt. Coupling capacitor value is 30 picofarad. So when we will solve this, we will get the value of omega t. We further know that omega is equals to 2 pi ft. So if we want to calculate the value of ft, we have to further divide this value with 2 pi. So it will become 0.19 milliampere per volt, 2 pi into 30 picofarad. When we will solve this value, it will come around 1 megahertz that we have already calculated with the help of frequency response curve. Okay. So this ft is called as unity gain frequency. Unity gain frequency, the frequency at which gain becomes 0 dB, or 0 dB is equals to 1. So in this video lecture, we have discussed the brief working of the internal circuit diagram of op-amp IC 741. Then we have seen how we can calculate the overall gain of op-amp IC 741. Practical ideal value is infinite and practical value is 243147, which is 107.7 dB. Then we have discussed the frequency response or the behavior of the op-amp IC with the change in frequency. It tends to be decreasing with the increase in frequency. The response or the gain of the op-amp start decreasing with the increase in frequency. But we can, up to certain points, we can compensate this value, which is called as frequency compensation. That can be done with the help of a coupling capacitor, which is connected internally in the second stage. And the type of technique we are using, Miller compensation technique. Then we have discussed the simplified model with the help of which we have calculated the value of unity gain bandwidth, which is 1 megahertz for op-amp IC 741. This is all about this video lecture. Thank you everyone.